Hi students, so let's discuss another important concept in biomechanical model of the atom is linear harmonic oscillators. So this is the last concept in this chapter. Okay, so what it is? A linear harmonic oscillators. So we know that what do you mean by a simple harmonic oscillator? So what is the meaning of a simple harmonic motion? So when you say that the object is basically a harmonic oscillator, a particle, what is a particle executes a simple harmonic motion about a mean positions is called a harmonic oscillators. The objects are what? The particle which executes a simple harmonic motion about its a mean position. Such objects, such particles are said to be what? A simple harmonic oscillator. Okay. So here, so what do you mean by simple harmonic motions? At any instant, what it is? At any instant, the accelerations of the particle is proportional to the displacement. What it is? The acceleration of the particle is proportional to the displacement and is directed towards the equilibrium positions or what is mean positions directed towards what is mean positions and what you can say about its what mean positions and what the equilibrium positions uh, is called as what is a simple harmonic motions. But motions are stated to what is a simple harmonic motions. Okay. What it is? At any instant of time, if the acceleration of the particle is proportional to the displacement and is always directed towards the mean position, then it is said to what a simple harmonic motion. Okay. The example for a simple harmonic motion are the oscillation of the simple pendulum. So whatever that simple pendulum is there, there is an example for our what? Simple harmonic motion. Okay. Or can call it what? The vibration of your what? The diatomic molecule or the vibration of the what? Atoms in the crystal lattice are the what? Few examples for what? Harmonic oscillators. So these are the particles which executes what produces a simple harmonic motion. So those particles we are calling it as simple harmonic motions. So here what we are doing is so we are what obtaining an equation for linear harmonic oscillator. So we are deriving an equations for what harmonic oscillator. Okay. So how to derive that equation? Let's see here. Consider a particle which is executing a simple harmonic motion. For one-dimensional harmonic oscillators, the restoring force, whatever that while moving towards one extreme end, a force is what generated inside the object. So that force we are calling it what a restoring force. The restoring force is proportional to the what a displacement and is directed towards the main position. So that's what simple harmonic motions. So therefore, whatever that restoring force is there that is produced inside that your object that is proportional to what a displacement. That's fine. So you write f is directly equal to what is x, and when you are removing that proportional sign, then giving what is one constant that here I'm calling it what k. So that negative sign indicates what this the negative sign indicates that the force and the displacement are what produced in opposite direction. Whatever the force and what the displacement are acting in what opposite directions to the significance of negative sign. Okay. So according to Newton's second law of motion, so we know that acceleration, acceleration, according to the definition of your F is nothing but m into d square x squared what d square, which is nothing but what force. That equals to m in area means this one, and a is d square x squared by d square is nothing but what acceleration. Okay, so m into d square x squared by d square equals to minus k into what is. Okay, so here, so we can obtain uh, the value of dx by dt. So we require dx by dt is there. So that needs to be obtained by using solution of the above equations. X is equal to a sine of what dt plus. So by differentiating this one twice with respect to t, so we can obtain what the value of your what dx by dt square. That is what required. So for in order to substitute inside is equal to square x is equal dt square. So this also obtained like the terms. So we know that another thing is Schrodinger one dimensional wave equation is given what rho square sine divided by rho x square plus of what 2m integrated what capital E minus of v, so into sine divided by h square, where h cross is equals to what h divided by what that is equals to 0. Okay, so see how that value of d square x divided by dt square is obtained. So we know that the potential energy of that particle when that particle is executing a simple harmonic motion. So v of x is equal to what integration of 0 to x. So here that the displacement object is extreme is taken what x, the distance moved by the your object from the mean position is what is x. Okay, so that's why is integrated. So what the potential energy possessed by that particle from what 0 to an x is what f of x into dx. Okay, the negative sign is there, but here the value of your f x is equals to what k into x is there, so that you want to substitute here. That already the negative sign is there, so that it becomes what minus into minus plus. So we are getting what kx into dx. So k is constant to take it outside, and the integration of x into dx is what? It's square divided by what? Okay. So this is the what? The potential energy possessed by what? Particle. So while executing in what? Simple harmonic motions along the revolving axis. Okay. For a particle executing a simple harmonic motion, so we know that this is according to the definition of SHM, m into d square x square dt square equals what? Minus k into x. Okay. If you make it class specification, it becomes what? D square x squared by dt square equals what? Minus of kx squared by what? Yeah. But k by m is taken as a constant, which is called what? Omega square, the angular velocity of that particle. Okay. So this what is k by m is equals to what is omega square, but we make extra specifications. Therefore, k is equals to what m into omega square, but omega is equals to what 2 pi into where mu is the frequency of what oscillation. Okay, it becomes what 4 pi square mu square into 1 m. This is the value of what it is k. It is so this value. So you are substituting the above equation. Okay, so therefore. So your our equation becomes the potential energy of the particle is given what v of x is equals to 1 by 2 4 pi square mu square m is what x square divided by 2 is the simplified part. So you will get it what? So 2 pi square and mu square x square into what? Yeah. Okay. Then so this value you want to insert in the equation of what is one minute. So you time in scoring time independent wave equation. So scoring time independent wave equation is given as dou square sine by dou x square. So plus of it is what 2m integrated is capital E minus of v divided by x square into sine equal to 0. So here the value of v is what? What to insert 2 pi square mu square x square and into sine divided by what? X cross square. Okay. So after inserting this one, now we want to substitute or make some adjustment. So you take that alpha is equal to 2 m by x square and beta is equal to what? 2 pi m divided by what? X star. Okay. So here, so here. So when you modify 2m to the inside, it becomes what? 2me into sine divided by what? X star square. So here, which one is taken? 2me by what? X star square is nothing but what? Alpha. And beta is equal to what? 2 pi mu m divided by x star square. So that's why that your above equation on introducing these variables, so that equation 1 becomes what is dou square sine divided by what is dou t square. So plus of what is alpha minus beta square into x square into psi equals what? 0. So on now you have to introduce one more new variable. So that's y is equal to what? Beta into x. Okay. So in order to have this one, so let us differentiate with respect to x. So dou psi by dou x equals to dou psi by dou y into dou y by dou x, because the given quantity is in variable of y equal to beta into x is there. So that's why. So that's why that's our equation. The representation can be done it like this: dou psi by dou y into dou y by what? Dou x. That is equals to what? So dou psi by dou y into differentiation of this quantity. Differentiation of this quantity with respect to what? X. You are getting what? Beta. So again, you are differentiate this quantity with respect to what? X. Twice. So the dou square side is what? Dou x square is equal to dou y. Dou x into what? Dou psi by dou x into. So you want here. I have left that beta. So beta is also what? Is introduced dou psi by. Okay, not it's already there. So dou y dou x into dou psi by dou x is there. Okay. So this is equal to dou by dou x into dou psi by dou y, which is what? Dou y by dou x. So this is equal to dou by dou y. So now you want to interchange that dou by is what? Dou y. So into dou psi by is what? So dou psi by dou y. So here the value of your dou psi by dou y is what is dou psi by. This is what is where is dou y by dou x. This is what dou y by dou x is there. So that value you want to insert here dou by dou y. So into what? Dou psi by is what is dou psi by dou y into beta. So into what? Dou y by what? And dou x is that. After this, so this one becomes what? So here, don't make it confusion. So this one is dou by dou x. This is dou psi by dou y into dou y by what is dou x is that. Okay. So when you do this one, you put it as it is. Dou psi by dou y is okay. Next is dou psi by dou y. Okay, dou psi by dou y. Dou psi by dou y into beta is there. So this is the value of what it is. So this is the value of which one? So that's the value of what? Dou y by dou x. That you want to insert that. This one, you don't write this. So you want to put it directly. So dou y. Okay, this is dou y is taken outside. So inside that you are getting a what it is. Uh, when it is dou y is taken outside, so inside that you are getting what? Dou psi y is what? Dou x is there. So this one instead of y, it should be what? X is. This is what it is. This one become what? Dou psi by dou x, but y it's not changed. So this y you want to change y to what? X. So that's your above equation becomes what? Beta into dou square side or dou y square. So on making corrections of what? This one, whatever here we change it. That is what? Dou y, dou x. Okay, into dou psi by dou y is there. Dou y by what? Dou x is there. So I'm interchanging this one. When it comes to this side, we take when we are taking this one, it becomes dou psi by dou x. So dou psi by dou x is that is what? Dou psi by dou y into a beta. So that's what insert it. Okay. After inserting this one, so your our equation, so that is what beta into rho square sine into what rho y square into this is what rho y bar rho x, that is equal to what beta into is what rho square sine into what rho y square into beta. Then so this value, so you have to insert in that your our equation. So it becomes what is, so that it becomes beta square beta square beta square into rho square side or what rho y square plus of what is alpha minus beta square into x square into what is a sum. That is equal to what is a 0. Okay, that is equal to what is 0. Beta square into rho square sine into what is rho y square. So plus of what? Uh, so on inserting these values, so it becomes beta square rho square sine by what rho y square plus of what alpha minus beta square into x square into psi is equal to what? This is 0. Okay, then this one you can make it tough to do this. Rho square sine is what? Rho y square plus of what? Alpha y beta square minus of what? X square into psi what? 0. Or you can introduce one more variable. Alpha by beta square, yeah, is equal towards lambda. So rho square sine, so rho y square plus of what? Lambda minus x square into what? Psi equal to 0. So this is the what? A simple equation for what? A linear harmonic oscillator. Okay. So simple derivation is there. Okay. Next. So from this, what is the use of predicting these equations in our quantum mechanics? So we have used what above variables. This for acceptable solution of the above equation is alpha bar beta is equals to what 2n plus 1 where n is what is integer, where n is an what integer. So then 2me divided by h star square 2me. So the value of alpha is what 2me by h star square. So that's divided by what? 2 pi mu m divided by what is that? That's cross. That is equals to what? 2n plus 1. Okay. So then E of n. Now you want to write this one. So E of n, you simplify this one. So you get what? E of n is equals to x cross pi mu x cross pi mu into bracket what? 2n plus 1. So that's equals to what? H divided by 2 pi into the value of x cross equals to what? H divided by 2 pi. 5 nu into bracket what 2n plus 1 that is equal to what? So h nu into bracket n plus 1 by 2. So it indicates that, so en is equals to, so we obtain what h nu into bracket n plus half. So it indicates that even at absolute zero temperature, the vibrational energy of the molecule, the vibrational energy of what? The molecular oscillator is not zero, but it is equal to what? 1 by 2. Actually, it is nothing but what? It is called as what? 0 point. So this is the what? The energy of our harmonic oscillators in the ground state. Whereas in case of quantum mechanics, if you substitute n is equals to 0, then the energy becomes what is 0. So according to old quantum theory, the energy is obtained. That's n is equals to 1. In case of eigenvalues of energy, E of n is equals to that is what n square h square, so divided what n ml square. So there, when you substitute n is equals to 0, that entire n becomes what? E of n is equals to 0 equals to what? 0. But in this case, so we're having what? Each atomic oscillators exhibits or possesses what? A certain amount of energy. So even though at what? At the zero, zero temperatures. Okay, so that energy, so here we are calling the word 0 point energy. Okay, so this is the equation for our what? Harmonic oscillators, that whatever that our one designates. The energy of the harmonic oscillators in the nth stage. So in the previous case, The energy of the our atomic oscillators in the n state is given what E of n is equal to what? N square h square divided by what is 8 ml square. Okay, so where n carries what n is equal to 0, 1, 2, 3, and so on, but there is n equal to 1, 2, 3, and so on. Okay, so this is the difference between the old quantum theory and what your linear harmonic oscillators. Okay, next the 0 point energy. This is already how mentioned in the our sentence itself. The first value of the what lowest energy state for the harmonic oscillators is obtained while taking words n is equals to 1. So when you substitute n is equals to 1, the quantity p of 0 equals to 1 by 2. N is equals to not 1, n is equals to 0. So substitute what? N is equals to what? 0. So we will get what? E of 0 is equals to 1 by 2 into h nu. So it is called as what? 0 point energy. And it is the energy of the ground state of our harmonic oscillator. Okay. So this is something about what is something about our what is 0 point energy. Okay. So here one more term is that is what it means by degeneracy state. Degeneracy state. The property of two or more quantum states. What is the property of two or more quantum states of a particle having different sets of what? Having what? Different sets of quantum numbers and different eigenfunctions. To have the same value of what? Momentum and energy is called as degeneration. Okay. So what is the property of what? Two or more quantum states of a particle having what? Different sets of quantum numbers, different sets of what? Quantum numbers and different eigenfunctions. Different eigenfunctions to have the same value of momentum in order to have a what same value of momentum energy is called as what degeneration. Okay, so this completes your what linear harmonic oscillators and something about what 0 point energy as well as what are the meaning of your degeneracy aspects. So that's the property of your two or what more quantum states of a particle having what different sets of quantum numbers and different what eigenfunctions in order to have the what same momentum and energy. It's called as what is degeneracy state. Okay, thank you.